Okay, so for our next discussion, we'll be continuing talking about still under the concept of resistance, lesson 2, and it's still under unit 1, introduction to electrical circuits. So in our previous discussion, we talked about the different factors that affects the resistance, and mainly, last discussions we talk about the physical factors that affects our resistance. In this discussion, we'll be talking another factor that affect our resistance, which is the temperature. In the previous one, we assumed that the temperature was constant for our resistivity. It's just 20 degrees Celsius, the table of our resistivity, meaning that resistivity is just equal to 20 degrees Celsius. This is only applicable for 20 degrees Celsius, not in a different temperature. So what happens if we change the temperature? What happens if we increase the temperature? What happens if we decrease the temperature? So basically what they did, they performed an experiment, and they took the measurement of the resistance while they are adjusting the temperature. So, and this is the result of that experiment. If this is R, our y-axis is the resistance, our x-axis is the temperature. So they're changing the temperature and they're measuring the actual resistance of the material. So initially, the relationship is just a straight line. But as they decrease and decrease, and by the way, this is the temperature should be in degrees Celsius. They did that in degrees Celsius. When they go lesser than 0 degrees Celsius and decrease the temperature further, they found out that the linear property will become like this one. So it's not directly intersect our x-axis or the temperature axis. And but if we try to infer that directly, that point where the function intersects with the x-axis or the temperature is called the inferred absolute zero temperature. So this is the inferred, we call it inferred zero resistance temperature, and we denote this one as capital T. So this is a temperature in degrees Celsius, and usually it's negative because this is zero. It goes beyond zero or less than 0 degrees Celsius. And the good thing is, this capital T, if they measure that one for every material, that T is also different. So it's a constant for every material. For a hard-drawn copper wire, the T is negative 240 degrees Celsius, wall 42. Or for an annealed one, it's 234 point something degrees Celsius. And I will be giving that table in our next discussion. But today, in this discussion, we'll be just deriving the formula that we'll be using. So in the other parts, it's just linear relationship. And we can exploit that so that we can derive the formula that describes the relationship between the resistance and the temperature. So now, if we take one point here, there's an equivalent temperature for that. And let's call that one R1. That's the resistance. And let's call the temperature T1. This is T1 from here to here, while R1 is the height. Then if we take another one here, and let's call this one R2. And there's an equivalent temperature also for that. Let's call it T2. And if you look at this figure, it's just a right triangle, two right triangles, this one and the other one. So there are just two right triangle, and we can also use that because there are two right triangles. It's just we can apply similar triangles because they are similar triangles, so to derive our formula. But before we do that, this length from here to here, this is also the inferred zero resistance temperature, capital T. So now, if we use similar triangles, if we divide R2 to R1, and that side, the corresponding side, which also must be, if they are similar, if we divide the bases of those corresponding sides should also be the same ratio. So if I divide R2 and R1, it should be equal to the equivalent, or the base equivalent for R2, the larger triangle, and that will be this length from here to here, and that is just T plus T2. While the length for the smaller triangle, that is just T plus T1. And this is our formula that we'll be using, where T is the inferred zero temperature, T1 is the initial temperature in degrees Celsius, initial temp in degrees Celsius, T2 is, this is the final or the new temperature in degrees Celsius, and the corresponding resistance for T1 is R1, corresponding resistance for T2 is R2. So this is the initial resistance or first resistance, and this is the new resistance in ohms. So that's the relationship. We can use that later on to solve the new resistance for a given material when we change the temperature. Now, there's another one. If we try to manipulate this equation further, I can do the partial fraction. I divide that T all over T plus T1, then add that with T2 all over T plus T1. So now, if I add plus T1 on the left side, I add T1, so I did change the equation, and to compensate that, I just need to subtract another T1 to the right side. Why do I do that? Because this will be equal to 1, and we can rewrite this R2 will be equal to R1 multiplied by that 1 plus 1 over T plus T1 multiplied, and this T2 minus T1, we can just make it delta T. Delta T meaning it's the change in temperature is equal to T2 minus T1. And there's another concept here. This coefficient here, we call it temperature coefficient. That one is called the temperature coefficient. And instead of using that, we can just change it into, we call it alpha. And the unit for this one is just per degree Celsius. So R2, the final formula now, will be equal to R1 multiplied by 1 plus alpha delta T. This is another formula for the new temperature if this is alpha 1. Remember, this is alpha 1. Meaning, this is alpha when the temperature is the temperature at R1. Because we derived that from 1 over T plus T1. So, alpha 1 is equal to 1 over T plus T1. And if that temperature changes, our alpha also changes. Why? Because T1 or the T will also change. So, in general, alpha N will be equal to 1 over T plus Tn. The formula for alpha N or the temperature coefficient will be with respect to the actual temperature, and also it is dependent to the zero resistance temperature, which is capital T, which is a constant for every material. So alpha will also become a constant for every material if we retain a constant temperature. And I'll be giving you also next discussion the different values for alpha for the different materials. So for now, remember these formulas for resistance and this other one. It depends on what is the given. If you're given with the zero inferred temperature, then use this one. But if you're given a temperature coefficient, you can directly use this formula. So I'll give you some examples in the next discussion.